Good morning, students. I would say I hope you're enjoying the cool weather, but it, as I always mention when I start class, we're getting back into that springtime element, and I don't really have an issue with it. I did enjoy the cool, but um, hopefully the weather that we have this week, which is probably not going to be the best, will improve as we get towards the final end of the term and the last week of class. Um, just remember that the window for the test number 4 is now open, and I've given you an extra day to go ahead and be flexible. So if you want to extend the time for test taking till tomorrow to give yourself a little bit of a breather, I know you have other exams and other classes to worry about. I don't want that to be an issue. Just make sure when you're done with your WebAssign part that you scan your work and submit that on Blackboard. You already know about that, so I won't go back into that. Um, so again, make sure that you have all this taken care of. I've delayed other homework assignments past the test information to later, to Sunday. Again, I want you to have some time to relax, not a lot, but just enough to feel like you're a human being. But don't completely shut down. Just remember that when you return, we'll complete the course, and you'll have some good mathematics under your belt. Now, what I want to do today is actually very interesting material. When you get to Calculus 2, you will spend quite a bit of time with sums and sequences. And a lot of the work that we do today will directly impact that because it's just a basic foundation for sequences and sums. So I will be able to give you some ideas about how you're going to use this in calculus. And I think you'll enjoy it. Just like the conic sections, it's a little different, but it's not as hard as the trigonometry. Trigonometry is very arithmetic. Sequences and sums are too, but we have different objects, the sines and cosines. So when we work with the conic sections and basically the sums and sequences, we're focused on algebraic techniques. So I hope you enjoy this today. I think it'll be a lot of fun. So let me share my screen. Now, just to set up some basic definition, I think, like I say, you've probably seen a lot of this maybe in a previous course where you were working in a general math setting or maybe in an algebra 2 setting. Lots of times sequences are introduced there, but if not, it won't matter. This will be a very natural discussion. So when we talk about a sequence in this class and mainly in your calculus class, you're going to be talking about real sequences. And when we talk about a real sequence, we're basically talking about a function f from the natural numbers into the real numbers. And when you would take your standardized tests, you'd always have what they called ordered lists. And then you try to figure out a pattern from the list and figure out what the next term would be. So that really defines a sequence. Now, again, sequences are just like functions. You can make them up to play whatever role you want in the problem you're actually solving. But the notation you have seen before, and we'll adopt that. For instance, when we look at f of 1, and notice here, usually it means that we will start with the natural number 1 and continue. Sometimes we may start an index at 0. Don't be alarmed by that. That's just a notational convenience. But for now, we'll stick with the 1 unless otherwise specified. So for instance, if we were interested in f of 1, you might think that we would write it just like that, f of 1. Well, the common notation is to use your favorite letter and subscript it. So with this notation, just like this, we know what the input is, and then the a sub 1 is the output. So an input of 1, a sub 1 output. So it's a 2 for the price of 1, just like this is, but this is a little bit cumbersome, whereas the subscript notation is easier. And so like the second number in the list would be f of 2. And we just keep going like this. F of 3, which is a sub 3. And so now, of course, when you get to the end, let me move Professor Ron over. Always too much of me to see and not enough room on my screen. We keep going to what we might think of as a general term, a sub n, f of n. But this is an infinite list. Now, of course, finite sequences are useful and we will deal with them. But when you get to calculus, most of everything will be extended to the infinite. And so that will be another bridge that you have to cross when you get there. We will talk about some infinite series today. That is a sum with an infinite number of terms, only because it will relate to the geometric sequence. So when we think about a particular example of this, let's just start with something geometric. Later on, we're just going to say more about this. So say we have an ordered list that looks like this: 1/3, 1/9, 1/27, 1/81. And then, of course, 3 times 81 is 243. So you know where I'm going with this. So this is an ordered list. This is a sequence. And so many times it might be the case where you just say, okay, well, I'm going to define my sequence by this list. Or you can just look at this and come up with some type of general term. Now, again, a general term rendering is not unique. It can have many different forms. So if you come up with a general term designation, it will be unique to you. But as long as it's valid, then the results will be the same, even if you have a colleague that has a different form. As long as the output is the same, you're good. So for instance, what we could do here is think that since we start with a 3, we could say a sub n is just 1/3 to the nth power, where n would be greater than or equal to 1. Because as we look here, to get to the next term, we multiplied by 1/3 to get 1/9. And so that's 1/3 squared. And then, of course, to get to the third term, that's 1/3 cubed. So we're seeing that this is a very simple way to define the actual sequence with this power function, so to speak. And well, not power, more exponential, because the base is fixed and the power is changing. So again, you know, you can change up the powers and use different exponents to meet whatever needs you have. But what I want to mention here is that this is a very special type of sequence. It's called geometric, and we're going to say more about that shortly. But I wanted to give you some simple examples of these sequences. Now, one thing that we like to do, you're thinking, you talk, Professor Ron, you say infinite series and you say sums. We're interested in sums that are generated by sequences. That is, we could think, well, what if we had a sum that was generated by this particular sequence? That is, we start adding the terms, like we take this term and we add it to this term and we add it to this term. And so we get a sum, so to speak. So how do we define that formally? So what we might do in this particular case is think about a partial sum. So for instance, we could say a sum with n terms and use a different variable. So we could say k equals 1 to n, where this n and this n are the same. And then we could say, okay, well, we're going to add up this. So this would be 1/3 to the k. So if we think about this, if we just expand it, now, of course, this is what we call the summation notation. Now, what does this mean? It means that we start with the index 1 and we replace k with 1, 1/3 to the first power. And then we add summand. The next summand will be k equal 2. And so 2 1/3 to the first power will add 1/3 to the second power. So to make this a little bit more formal, this means start with index 1, 1/3, and then index 2. So I'll just write these under here. K equal 2. That's going to be a 1/9. And then k equal 3, 1 over 27. And then we just ellipsis till we have the value k equal n, which will be 1/3 to the n. So we think about this as a partial sum. Now, when we actually write the geometric sum, our notation may vary a little bit, but it'll still be the same. So when we look at this, we're thinking this is what we call the nth partial sum. Nth partial sum. That means we take a sequence and we add the first n terms. So you might look at this and say, oh, okay, so this shorthand notation represents this finite sum here. So it might be convenient in our work to be able to write this way to make our computations a little bit easier. And then, of course, we can manipulate sums, and I'll say things about that. So let's just look at some sums, some partial sums. Let's do S1. Well, in this case, we just have k equal 1 to 1. So that's just one term right there. So the first partial sum would just be 1/3. Sequences are easy. The theory is really with the sums, even though you'll do some more sequence theory when you get to calculus, but that'll be in the realm of calculus. So now S2 would say we would just add the first two terms. So we'll say 1/3 plus 1/9. So we can get a common denominator. So that'll be a 3 plus 1, or 4 over 9. So that would be what we would call the second partial sum. Let's just do a few more, just so you get the hang of this. Say we want to add the first three terms. Well, once we know the sum of these, we don't have to back up. So we'll just say this is 1/3 plus 1/9 plus 1 over 27. And you're thinking, well, it would be nice if we just had a formula for this, and we will see one. Now we know what these two are. We can just use parentheses here. This will be 4/9 plus 1 over 27. Get a common denominator. So that'll be a 3. So that's a 12 plus a 1. So we get 13 over 27. So let's do one more. So the idea here is that the partial sums are recursive unless we can find a nice formula for the partial sum to lessen our work. So when we look at this, we're thinking if we want to add the first four terms, let's just write it out in expanded form. 1/3 plus 1/9 plus 1 over 27 plus 1 over 81. And so now we know the first three terms. So that's 13 over 27 plus 1 over 81. So we can get a common denominator. And so 27, that'll be a 3 times a 13. That's a 39 plus a 1. So this will be a 40 divided by 81. So again, our question might be if we actually start creating partial sums. For instance, if you look at this sequence here, you're thinking, does this sequence have a limit? And your intuition would probably say yes, because as n gets larger and larger, the denominator gets larger and larger. The numerator is fixed at 1. So as this denominator gets larger and larger, you're dividing 1 by what becomes a very large number. And as the number gets larger and larger, that particular ratio will get closer and closer to 0 from above. It'll just slide into 0. So we would intuitively think that the limit of this sequence would be 0. And of course, you'll do some arithmetic and calculus to prove that. Likewise, we could look at the sequence here. For instance, we think of this as a new sequence. First term of the sequence, second term of the sequence, third, fourth. So we can think of this as a sequence of partial sums. So you're thinking, when we refer to a sequence, sorry, my nose is itching, good old allergies. when we think of a sequence, we can just denote it this way, or we could think of a sequence of partial sums and just denote it this way. Sometimes we'll put them in curly braces. But what we see here is that we might ask the question, would it be possible for this sequence of the partial sums to actually have a limit? And that would be basically how we configure the infinite series converging. So we take a sequence and we make a new sequence by creating a sequence of partial sums. So we might say that if we have something like this, k equal 1 to infinity, 1/3 k, this would actually be the limit as n approaches infinity of s sub n. So if we let n pass to infinity, then now this becomes infinite. So we call this an infinite series, infinite series. And so we would have to study this to figure out whether or not this actually had a finite limit. And so that's really an interesting topic when you think about adding an infinite number of terms, thinking that, well, these terms that we add, I mean, these sequential terms are getting smaller and smaller. So it might make some sense that it could possibly converge as long as these are getting small fast enough. So this is the idea that we want to think about. This is why we study sequences and partial sums at all. Otherwise, it really would be quite a waste of time. So we're going to figure out a formula for this. So while we're at it, let's just go ahead and figure out a formula for the geometric partial sum. So here's our little exercise. And then we'll talk about some telescoping sums. A lot of the problems are really simple, but the partial sums are where the content actually is. So now let's just look at a regular geometric sequence. Say we take an A non-zero and an R non-zero. So we don't really want R to be 1. So we'll just say in parentheses, we're really not interested when R is 1. But non-zero A and non-zero R. And then we can consider the following sequence, which will be geometric. So we're going to say geometric. So all of this is tied together, and I like to do it in a little bit different order so it makes sense, so it doesn't look like we're just plodding along doing worthless exercises. So we might say the first term is A, and this is, ladies and gentlemen, this is a standard notation. So we have conventions just like with the conic sections, and we'll do the same with the geometric. But remember, every time you read a book, look at their conventions and see how they write things. What you know will be equivalent to what's written in the book, but there may be notational differences. Then we'll multiply by R. Then we'll multiply by another R. Multiply by another R. And now what I was saying before, if we consider this to be the first term, first, second, then the nth term will be AR n minus 1. So we start with the first term, R to the 0, and then we get to the nth term, we have AR to the n minus 1. And so now, when we look at this, we're thinking, okay, well, we've got a general term here, just like we had in the previous one. So we can say A sub n will be AR to the n minus 1 as the general term. And what we can see will take n greater than or equal to 1. So when n is 1, we get AR to the 0, which is A times 1, which is A. And then when n is equal to 2, we get AR to the first, which is this term. So this would be a convenient general term. So this is standard. And again, you can be creative with the powers as long as the output is the same. Now, with the geometric partial sum, there's a really nice interplay here. This is how I'm going to introduce what we call a telescoping sum. So what we want to do is think, okay, what would the partial sum look like? So when we look at a partial sum, we're just adding n of these terms. So let's take the general term and switch to an index k. So we'll have n equals 1, or excuse me, k, we need k, 2n, a, r to the k minus 1. So now, again, this does the same thing. This just adds n terms. When k is equal to 1, we just get a, and k is equal to 2, we get ar. So again, since we're using the n here, we really can't use the same letter here. That would be unclear. So we've got this. And now what we want to do is perform a little bit of algebra on this. So note, consider, and we'll use some properties of sums, which are very simple. Consider, in this case, S sub n minus r times S sub n. That is, we're going to take this sum and multiply it by r. So first, what we can see is that a formula for S sub n can be factored, and this will give us 1 minus r. Okay, that's just simple algebra. And you're thinking, when we look at this, why? Why would Professor Ron do this? Well, we get what we call a telescoping sum from this when most of the terms that we generate will absorb. We'll get a bunch of zeros and we'll just be left with a few terms. So now let's just see how we get that. So let's write these out. So the first one is just S sub n, which is this, k equals 1 to n, a r k minus 1. And then the next term, we're just going to multiply by r. So when we run the r in, this will be a k minus 1 plus 1, which gives us r to the k. So we have r to the k. Now, when we look at this, it's like, well, do we have to write all this out and try to figure out what we get? Well, that's a little bit cumbersome. So I'm going to show you a technique that we learned in this class to get the powers equal. So notice, we would love to be able to subtract these two series because they're just finite. You can multiply them by numbers, you can subtract them and add them, but the terms have to be the same, just like you're adding polynomials. So we would want this power to be k like it would be here. So what we're going to do is we're going to replace k with k minus 1. So I'll write that in red. So replace k with, or excuse me, k minus 1 with k. K minus 1 with k. So now if we make this bigger by 1, we have to make this smaller by 1. So just, you know, pay the piper, like adding 1 and subtracting 1. So now we'll have k equals 0 up to now n minus 1, a r k. Now when you see k is equal to 0, we just get a, just like we get a when k is equal to 1. So these two are equivalent. So we essentially re-indexed, replace k minus 1 with k. And now, of course, we can write this and figure out the straggling terms. Now, basically, these two series are equal, but this has a 0 term and this has an nth term. So let's just pull those away, and then what will be left behind will be the same. So let's write the k equals 0 term here, which of course is just a. So this is very simple if you just think about dealing with the algebra of polynomials, which we've done too many times. And now over here, we're going to subtract, but notice this has an nth term. So when k is equal to n, we get arn to the nth power. So we'll get minus k equals 1 to n minus 1 ark. And then, of course, that top, very top term is arn. So this is the k equals 0 term from this series, and this is the k equal n term. So now what you're seeing is what I told you would happen. Once we make sure we have like terms, we can subtract all of these. Now notice this right in here, this is just 0 because we're subtracting the same partial sum from itself. So that's why I did that. So when you say why, a lot of times when you investigate things, you're trying to figure out how you can configure things in a way to make it more useful, because this way we don't have to sit here and do what we did before. This is kind of painful if this is the only route we have, and sometimes it is. That's where computers are very nice. But with the geometric, we'll basically generate a formula. So now all of this absorbs, this goes away. So we're left with, we just set this equal. That is equivalently Sn times 1 minus r equals, now what are we left with? A minus a r to the n. But of course we factor things to death, and this is just a times 1 minus r to the n. Just like doing conic sections, it's all exact computation. Like I say, it is so simple to check your work. I mean, I can remember yesterday when I was doing a computation during the office hours, conference hours, I had a slip up in some arithmetic. And so I just went back and checked it. And of course, I had treated a product like a sum for some reason. We all have these brain freezes, but the exact computation says, okay, let me check this. Let me see what I've done here. And you can figure out where you make an error. That's why when I teach you to do exact computation, I'm teaching you to do what I do myself. And it is the way to do STEM mathematics. So now look, we have a formula for the partial sum. That is S of n will now be a times 1 minus r to the n divided by 1 minus r. That's why I didn't really care that we have r equal to 1. That'd be kind of an issue here. So now, not only do we have a formula for the general term, we have a formula for the partial sum. So the idea here is that if you know the a and the r, you can get the partial sum. So like for instance, on the very last problem that we did, notice we had an S4 here. Let's write this down just as a way to look at this. So here, I'll leave this up so you've got this. I'll just do this to the side. So in the previous problem, notice that the A, the very first term, was 1/3. That was the very first term, the A right here. And then of course the R was also 1/3. I mean, kind of repetitive, right? And so now when we do S4, we can just say 1/3. And then we have 1 minus 1/3 to the 4th divided by 1 minus 1/3. Okay? So now when we look at this, we have 1/3, and this will be 3 to the 4th, which will be what, 81. So we have 1 minus 1 over 81. And of course, 1 minus 1/3 is 2/3. So now I'll move the computation over here. So let's get a 1/3 divided by 2/3. We'll write that off here. That's of course just going to be 1/2. And then we get common denominator of 81. So this will be 81 minus 1. And now when we actually look at this, we're thinking, okay, so notice here, this gives us an 80 over 81. And then of course the 1/2 survives because these absorb. So this is times 1/2. And that just gives us 40 over 81, which is what we got when we just added things piece by piece. So the key here is if this n gets fairly large, then we can use our Google calculator if we need, but we've got an exact sum. It's not an approximation. Now, there's nothing wrong with approximations. We have to do that in calculus because we may not be able to sum the series, but we can, to whatever degree accuracy, compute a good sum that we can use to build a bridge or something. So the idea here with the geometric, it's very special. It's like the Pythagorean theorem. It's like, you know, we think about things that if we didn't have, we'd be in trouble. This is one of those series, the geometric. Now, one thing I want to do is now just kind of recast this with an infinite sum and then talk about the arithmetic and some of the nice formulas that we get. So now, just as a little aside, we see, we'll just complete this, we have S of n is equal to A times 1 minus R to the n divided by 1 minus R. And so this is something you're going to learn in calculus. But if R in absolute value is less than 1, this implies that the limit as n passes to infinity of R sub n will be 0. And I'll show you how to prove that when you get to calculus. That is, you raise a number between -1 and 1 to higher and higher powers, it will converge to 0. At least intuitively, that makes sense, like 1/3 to higher and higher powers. That intuitively makes sense. So this implies that, like I wrote before, the infinite sum, so we can say, now I'll just switch to n equals 1 to infinity of AR to the n minus 1. That's the partial sum. So basically, this is the limit as n passes to infinity of our partial sum. That will now just be A divided by 1 minus R because that term will tend to 0 here. So we get A over 1 minus R. So we can actually sum the infinite geometric series as long as the R, and what is R usually called? It's usually called the common ratio. Common ratio is what we usually call R. You can just call it R if you want, but it's the common ratio because as you move from one term to the next, you multiply by R, the common ratio. So now what we see is we have a partial sum formula which can be extended to the infinite series sum formula as long as the R in absolute value is less than 1. Now, if it equals 1 or bigger in absolute value than 1, it diverges. That's what we say that the series does not converge in the sense that it either oscillates but just jumps around or becomes positively infinite or negatively infinite. The thing is, when a series converges, the outputs get closer and closer and closer to a finite number. That's what we mean for something to have a limit. You don't necessarily get there, but the more terms you get closer and closer and closer, just like this being limit 0. As n gets larger and larger, the output is closer and closer to 0. And that's what you will do in calculus when you do the arithmetic of that. Now, so that's one sequence. What's another sequence that will be useful? Well, we want to talk about it, and it's going to be called the arithmetic. The geometric is like the easiest one to do because it's so natural. You've seen geometric sequences all the time. So now what we want to do is look at a few what I call famous formulas. So these are the famous formulas, which I call their partial sums. I had to come up with a name one time, partial sums, and I don't know how these are so much famous, but they're used in calculus. And so these can be generated for any value of n. They're very famous. So let me write a couple of these down. The first one will just be like if we have, say, some number C, and usually we'll just take C to be non-zero. So we'll take C to be non-zero. And let's say we'll just say K equals 1 to N. This is just a simple deal. It's nothing difficult. This is basically saying add C to itself N times. So this is just C plus C plus C plus C for N sum Ns. So this is just N times C. That comes up quite often. So for instance, if we had something like this, say K equals 1 to 100 of 2, that would just be 2 times 100 or 200. You just add N to itself or 2 to itself 100 times. So that's easy. And then of course, because like we saw with the geometric derivation of the partial sum, we can add finite series or partial sums just like we're adding polynomials. And then of course, infinite series, as long as they converge, can be added, subtracted, even multiplied and divided. Now, one of the formulas we're going to need for the arithmetic in a minute, I'll just use, now I guess I can use K again. K equals 1 to N of K. This just means you add 1 plus 2 plus 3 plus 4 up to N. This has a very famous formula, and these can be easily proven by induction or by algebraic means. So if we add the first N counting numbers, like 1 up to 10, the formula is closed like it is here. It's N times N plus 1 over 2. So this is very useful. Again, these can be generated for varying powers of K, K to the first, K to the second, K to the third. Computers can algorithmically generate these formulas, but we can do them all by hand. And then of course, we'll prove some of these by induction later. That'll be a nice proof method that we talk about. Now, the third one, and this come up quite often in the calculus, we can sum the first N squares. And this has a fairly interesting formula. N times N plus 1 times 2N plus 1 divided by 6. So if we sum 1 squared plus 2 squared plus 3 squared plus 4 squared, then we can just replace N with 4. And then we've got the partial sum. Again, just like we did here with geometric or these two guys. So these are nice closed formulas for partial sums. And then the fourth one that we use, and of course there are infinitely many of these, but I'm writing down the ones that we will use in the calculus. Cube. And it just turns out to be the square of this formula here. That is N squared times N plus 1 quantity squared divided by 4. So these are what we call the famous formulas. And we can use the algebra of sums to do simple computations. Now, we've talked about the telescoping, and those are kind of easy to see, but let's just do a simple computation here. For instance, if we had something like this, say we have K equals 1 to say 15 of, and we'll say 2K squared plus 5. Now you're thinking, okay, Professor Ron, I could just add all of this up, put K equal 1 and then K equal 2 and add it all, and that's fine. And that would certainly be a way to do it, but maybe not terribly efficient. So now we're thinking, just like this is convergent because it's finite, so we can break it up into pieces. Just like using the fact that we can add and subtract series, finite sums, we can break this up into pieces and make it manageable and use one of the famous formulas. So now, first, this will give us, and this just basically means we can factor the C. So this will be K equals 1 to 15 of 2K squared plus k equals 1 to 15 of 5. Now, the 2, like I said here, this one, we know what this one is. This 2 here can always be factored. We can leave it in there, but it has no impact on, or no dependence on the k. So then we can say, now we can use one of the famous formulas. So this will be 2 times the sum of k equals 1 to 15 of k squared. And then, of course, this is just number 1 here, which is 15 times 5, NC. Add 5 to itself 15 times. So 15 times 5. So now we've got our famous formula here. Again, n is 15, so we'll use it. So we have 2. We'll just leave that on the outside. So we'll have 15. And then 15 plus 1 is 16. And then we're going to say 2 times 15, which is 30 plus 1, gives us a 31. So again, n, 15, n plus 1, 16, and 2n, which is 30 plus 1, 31. Divide by what? 6, famous formula. Plus, I'll just write this as 5 times 15. So now notice we get some absorbing terms. I mean, first we have a 1/3. You're thinking, well, I've got this 15 here, I can use that, but I probably am not. Notice here, if you like, I'll go ahead and do this. I'll put the 6 here, but I'll write it as what? 2 times 3. So now we can see the 2 will absorb here, so that's gone, and the 3 will absorb into the 5, 15, and give us a 5. So this will be a 5 times 16 times a 31. So the 6 is 2 times 3, 2 into 2, that'll give us 1, and 3 into 15 will give us a 5. So 5 times 16 times 31 plus 5 times 15. So now we can factor this. So this will be a 5. So we have a 16 times a 31 plus, in this case, a 15. So now we'll break this down into simple numbers. So this will be a 5. And so we have a 16 times a 30 plus a 1 plus a 15. So this will give us 5. And now the 0 we have. And then, of course, 3 times 6, that's an 18, plus a 1, that's 48. So in this case, 480. And then, of course, 16 times 1 is 16, plus 15. So this will give us 5 times 480. And of course, that's a 31 right there. So we have 5. So when we add, we get a 1. And then, of course, a 3 and an 8, that's an 11. Carry the 1, 5, 11. And then multiply by 5, we get 5, 5, 25. So again, when you have closed form partial sum formulas like we have here, you can break this down into pieces and then use what we call the famous formulas. So we get 2,555, just breaking this down into pieces using the formulas here. Again, you can always write this down and check it off one by one, but this kind of manipulation is what you're going to do in Calculus 1 and in Calculus 2. So it's a good place to start here, just by breaking this down into pieces and then utilizing formulas that are convenient. Again, when you do Riemann sums in Calculus 1, you will do this. So this is kind of a neat way to say, okay, well, you know, I've got a formula here that's basically a number. That is, I look at this and say, that's a number because I've got K running from 1 to 15. I've got 15 terms of this partial sum. This sequence is the generating sequence right here, and we want to add 15 of the terms. So we get it through just exact computation using the famous formulas. Now we want to use this one in the next example. So this is a good example just to kind of get your feet wet with manipulating finite sums. Remember, a finite sum is always converging because you can add the terms and you get a number. It's the infinite case that's difficult. That's what you spend time on in the calculus. So now, let's look at another type of sequence and do the same thing. So this is called the arithmetic. Now the telescoping is fun, and I want you to look in your WebAssign and be on the outlook for the telescoping. Those are fun sums to compute when everything just goes away. So look for patterns. That's how you find these things. With arithmetic, we're going to say A is non-zero and D is non-zero. I don't really care if D equals 1, but I don't really think it's very interesting when they're 0. So then we want to look at the following sequence. This is not very interesting, at least not as interesting as the geometric, but it does occur. So I want you to know about it. This sequence, instead of multiplying by R, we're going to add D. So what we're going to say, D is often called, instead of common ratio, it'll be the common difference, and it can be any number. So we're going to say the first term is A, and then we're going to add D to A to generate the second term. So this is very simple, very similar to the geometric. And then we're going to add another copy of D. So A plus 2D, and we just keep doing that. So you're thinking, oh, well, is this going to have a special form? Well, it will. Now, of course, this is what we call the first term, the second term, the third term, etc. And so we can ellipse down to the what? The nth term. And so this would be what? N minus 1 times D. Just like we had R to the N minus 1. This would be the nth term, etc. Now, of course, this is really not the best. When you look at something like this, you know, you're adding the same number every time, and it's not changing. When you're multiplying by R and it's between -1 and 1, then there is a change occurring. The powers of R are getting smaller. They're dragging the output down, so to speak. They're making the output smaller in the sense that there's a decreasing sensation going on when you basically start adding smaller and smaller bits. Here, you keep adding the same thing every time. So this doesn't have the convergence that the geometric would have. So it's not as interesting, but it, like I say, it's still important. Now, so we can see that the nth term will be A plus N minus 1 times D. So that's the nth term. So the first term, you don't add any D, you just get 0 times D, you get A. For the second term, you get what, 2 minus 1, so you get A plus D. So this is a very convenient formula, which we get from here just by looking at the form of the sequence. And now what about a partial sum? So we can actually do that. So let's look at the partial sum and use the technique that I used on the last problem. So that's why I did that. So we'll say, what about the partial sum? Well, this will be K equals 1 to N. We always switch to K because this means add the first N terms. And so what's this going to look like? Let's do the little focus. There we go. It looks a little better. So now we have it right here. So we've got what? A plus, now we have K minus 1 times D. So now when we look at this, it's like, well, can we use the same technique that we used before? And we certainly can, because we just break this up into two pieces. Now notice, just like with the last one, we'll have the sum K equals 1 to N of A, excuse me, plus, and now of course we're going to sum this, but notice the D is just a constant. So like we had it before, we can factor the D. So we have D, K equals 1 to N of K minus 1. Now, what we see here, and this is interesting, and then you're thinking, well, can we make this even simpler? Well, we're not going to break this up more, because I'm going to show you a trick to get at what this is. Now, this is just adding A to itself N times. That's N times A. Now, if we look at the second part, this is basically the famous formula, but now we don't extend to N, we only extend to N minus 1. So we start with 1 and we ascend to N minus 1. So we can just replace N in the formula with N minus 1 without having to break this up and do a lot of excessive work. So now we're thinking, okay, this will be 1/2 times N minus 1 times N times D. So remember, and I'll write it so it looks a little bit more user-friendly. Let me put the 2 in the denominator so it looks like the formula I gave you before. So we've got that. So instead of N times N plus 1 times D, we're only ascending to N minus 1. So we replace N with N minus 1 in the famous formula. And that makes it a little bit easier than breaking that up. So that's just a measure of convenience. That's, well, all of my proofs are Professor Ron, but that's called just being efficient. So now, if we look at this and we're thinking, how can we make this look nicer? Convention here says to basically extract, that is, when you see the conventional formula for the partial sum, you extract N over 2. So notice we have an N over 2 here. And then, of course, if we put in a 2 and pay for it, we have an N over 2 right here. So let's do that. Again, this is convention, like doing the conic sections. So we have N over 2, and that leaves behind a 2A. And then, of course, we just have what? Plus N minus 1 times D. Now that's a formula right there that's a standard formula. That is the partial sum for the arithmetic partial sum, or the formula for the partial sum for the arithmetic sequence will now be N over 2 times the quantity 2A plus N minus 1 times the complement difference. Which again, if you know like the A and the R and the geometric, you know the A and the D and the N, and you substitute that in. The same thing. Now, this is one form. The other form would be, so I'll summarize this, but now you can break this up into A plus A and rewrite this. So we have A, which is the first term, and then put the A with this, which will give us the nth term. So there's a reason we factor the N over 2 to give us a nice formula. So now this can also be written as the first term plus the nth term right here. So we can say A plus A sub n. That's another way to do it. And if you like, you know, if you wanna call that like an A sub 1, you can, but since we're using A, we know that's the first term. So here's another way to do it. You could think the partial sum will just be written this form. If you know N, you know, and you want to, or it's easy to figure out the last term, then use it. But if you don't, it's no problem. So in the summary, we can say the partial sum for the arithmetic sequence can be written this way: n over 2 times 2a plus n minus 1 times d, or, and of course I could just write equals, but I want to specify that they're equivalent, but I don't want you to run them together. You'll use one or the other. We'll just have a plus a sub n. So either of these will work depending on the context. So this is the formula for the partial sum of the arithmetic sequence. These are the partial sums, okay? So again, just like geometric, we can use the power of these formulas to make our work a little bit easier. And there is nothing wrong with that. So let's look at some examples. I always have too many examples. So let's try some of these, and then we'll do some geometric. So let's apply this. So when it comes to sequences, we like partial sums. So for instance, here's an example from your WebAssign. It says we have a stack of poles. Sometimes you go into these industrial yards and you see stacks of things in like nice geometric shapes. So we've got the first layer of poles on the bottom. We have 26 poles. For the second layer, we have 25 poles. For the third layer, we have 24 poles. So etc. So basically, for each layer, the number of poles decreases by 1. And there are, this is what WebAssign gives us, there are 16 layers. And here's the question: how many poles are there? Compute the number of poles. Now, of course, you could just say, well, just start adding 26 plus 25 plus 24 and do that. There's absolutely nothing wrong with that. But you know, if you've got a whole bunch of layers and you start doing that, that might be a little bit cumbersome. So first, we think, so compute the number of poles. We think arithmetic. So now when we think about this, we see that the first term, so here's the sequence: 26, that's the first term, 25, 24. And we keep going until we look at this and we say 26 plus, now of course, the D is, we're subtracting, so I need a minus here. So we have minus n minus 1 times a 1. So in this particular case, I guess I could just say plus and put the minus here. That way you can see that we're adding -1. That might be a better way to do it, to keep it consistent with the theory that I've given you. So now let's just write over here. A is 26. The common difference is -1. That way this looks exactly as I've written it every time. So A plus n minus 1 times the D. So that keeps it consistent. So this is really what we have. So now we say, okay, and then of course, if you want to add n equals 16. So, you know, we can be real lazy. So now if we want to think about this, we can say the last term will be A, in this case, plus, and I'll write it down, N minus 1 times D. Well, let me just do this. Let me just write the general formula, and then I'll put in all the numbers. So here I've got it all mapped out. So this implies, or equivalently, so here's the formula that we need to use. Notice these correspond. So this will give us A sub 16 will be 26 plus 16. Now, of course, you could reduce this, but it doesn't matter. Just let the algebra do the work. Minus 1 times a negative 1. So we get 26 plus, in this case, 15 times what? A negative 1. So this is 26 minus 15. So that'll give us a 1 and a 1, an 11. So now we have the nth term, so to speak, the 16th term. So this implies that S sub 16 will go here, use this formula. And let me just write this up here. It's always good to write down the formulas you're using. N over 2, A plus AN. So now we get 16 over 2, and we get 26 plus 11. So this gives us an 8, and then we have what? We got a 7, 37. So we have a 56, and then a 5, 296. Now, you might be thinking, well, you know, it's a lot to think about the theory here, but what I would recommend, and this is what I keep saying, just kind of write down the formulas until you get used to them, and then fill them in. But notice here, this was Professor Ron's choice, just to say, okay, well, if I, for instance, I'm told how many elements there are, there's 16. So I can go ahead and figure out the nth or the 16th term and just use this formula, which actually is pretty simple. And so it wasn't difficult to go ahead and figure out how many poles are in the last one, just algebraically. You don't have to guess, and you don't have to count on your fingers. You just let the theory do the work. And so once you have that, you can just substitute, and the arithmetic is very simple. So the stack of poles would in this particular case, contain 296 poles. So not very difficult, but an interesting problem. Now, let's look at some examples with the geometric. So we can do another partial sum. So I have several examples here, some from your web assignment. Let's see here. We'll do just some basic computational ones first. So let's just say, let's start with, let's see here. Let's just do one of these where we have a very basic setup. Now, the geometric are more that we would do in the calculus. And so let's write a geometric sequence down and then do the algebra to figure out what the partial sum is. And this is written in expanded form. 1 minus 1/2 plus 1/4 minus 1/8. Now we get plus ... minus 1 over 512. So when you look at this, you're thinking, okay, well, let's just kind of look here. We see that the first term is 1. And to get from 1 to the second term, we multiply by a negative 1/2. And then, of course, negative 1/2 times negative 1/2 is positive 1/4. So we can see that this is geometric. So we want, what is this? What is this sum? Compute the sum. Compute the sum. This is not a trivial problem. So now we think, okay, well, in this particular case, we want to look at this in terms of a general term. So for instance, we know a sub n equals a r to the n minus 1. So equivalently, we'd have a sub n equals negative 1/2 to the n minus 1. Now, notice in this particular case that this is negative. This is less than 0. And so that just means that n minus 1 must be odd. This implies, at least for this sequence, for the nth term, n minus 1 is odd for term negative 1 over 5/12. So we expect our value for n to be an even number because we're just going to have to add 1 to it. So that's kind of a little plus there. So now we'll say, let's find the nth term. Let's compute n. So we say, what is n? So we say, in this case, negative 1/2 to the n minus 1 equals negative 1 over 5/12. Now, when you look at this and you think about what this means in terms of algebra, the negatives we don't have to worry about. We now know that n minus 1 is odd, but we just need to focus on the powers of 2. So equivalently, if you reciprocate everything, we have 2 to the n minus 1 equals 5/12, just focusing on the denominators. So at this point, we're thinking, okay, this is nice because this is a power of 2, so we're not going to have logarithms in our answer. So first, this is 2 times 256. These are easy numbers. So again, this is doable in the sense that we can apply the theory directly. And so, of course, 16 times 16. So this is 2 times 16 times 16. So don't get caught up with all the negatives. That's kind of a little sidebar. So we want to focus on what n is and then use this to make sure that our work is correct. And so, of course, that's 2 to the 4th, right? So this is 2 to the 1st times 2 to the 4th times 2 to the 4th. Add up all the powers, we get 2 to the 9th. So in this case, it is indeed true. N minus 1 equals 9, as we knew would have to be the case. So if and only if n equals 10. So when you apply the theory and you think about the fact that, oh man, I've got a negative power. How am I going to do that on a negative term? Focus on the absolute value, so to speak, to compute the n, and then you can verify that this is right. So if we had an error here, that'd be an odd number, and then we say, oh, something's wrong, okay? So now we verified what n is, and now we've got the formula. So let's remind ourselves, S sub n, it's better to write the formula down than to try to put n equals this, r equals this, a equals this. That gets a bit cumbersome. So just say, okay, well, here's the formula. This is a times 1 minus r to the n divided by 1 minus r. So we get S sub 10. This is S sub 10. This is the sum of the first 10 terms of this sequence. So that's why we have to find n in order to use this. So now a is 1, so that's nice. So we just 1. So 1 minus, and now we have a negative 1/2 to the 10th power. And now downstairs, we have 1 minus a negative 1/2. Remember, r is negative 1/2. So when we look at this, the negative will absorb because of the even power. Remember, alternating. I'll do another example with some alternating signs. So this is going to be 1 minus 1 over 2 to the 10th. Now, of course, minus minus, that'll be 3/2. So we kind of know what's going on here. In this particular case, we can say, okay, well, what is this? I mean, what is this number? So 2 to the 9th gives us the 512. So if we hit this with another 2, that is, just note 2 to the 10th will just be 2 times 512, which is 1,024. So that's nice to know, knowing that we've done this calculation. So we have 1 minus 1 over 1,024 divided by 3/2. So now we can just take the 3/2 over to the side, get it out of the way. Well, let me put it in a way that's correct. Get it out of the way by reciprocating it. 1 over 3/2 is just 2/3. So let's write it in a form that won't get us into trouble. And then we have 1,024. So this is 1,024 minus 1. So we have 2/3 times 1,023 divided by 1,024. Now again, you start looking at this and you say, okay, well, I guess we're all right. The 2 into 1,024 is 512. And then the sum of the digits here is 6, so it's divisible by 3. So that'll give us a 3, so a 12, so that's a 4 and a 1. And now when you look at this, let's see, that's an 8, so that's not divisible by 3. This is a power of 2, that's not a power of 2, so we're done. So the sum here geometrically is doable, but we see that utilizing the theory means that we have to figure out n, and that can be a daunting task. So partial sums, students don't like partial sums with the geometric. They like the infinite series because those are easy. The n is gone. The n went to infinity, so there's no n in the formula. So all the Calculus 2 students love the infinite geometric series because they don't have to worry about n, and you will too. So the harder problem, at least here, is to look at this. So now what we can think of, like in terms of a power series, which you're going to do in calculus, we can think of a series or geometric series that looks like this. So we could say 1, where we get variable x, x squared, x cubed, and then we can, in this particular case, we can call this the first term. We can call this the second term. So the nth term would be just x to the n minus 1, etc. So now here's just a little aside, a geometric sequence. So we can say a sub n is equal to 1 times x to the n minus 1. And of course, if x in absolute value is less than 1, this would be convergent in the infinite case. So we could say now that s sub infinity would just be, if you like, n equals 1 to infinity of x to the n minus 1. Now, of course, we can look at this and say, if we make this smaller, start this at 0, we make this bigger by 1. So we could re-index and just say n equals 0 to infinity of x to the n. Now, of course, in this case, this is the infinite sum. So this is a divided by 1 minus r. So as a power series, this is geometric. And this is pivotal in the study of infinite series. My students in Cal 2 will struggle with this because they didn't maybe get all of this in pre-cal. But the idea is that the utility of the geometric series cannot be underestimated. As a power series, it opens the door to computations that will illuminate, inverse trig functions, the natural logarithm. I mean, it's amazing what you can do with it. And so this basically shows you that when you look at the infinite case and the actual common ratio in absolute value is less than 1, you get a very nice formula for the infinite series, which can be manipulated to produce power series for different types of functions, and it's extremely powerful. So I don't want you to get to Cal 2 and just say, well, I've never seen that before. You will have seen this, but in the context of the calculus, you can see what you can do with it. So that's really the main point there. So very good. Now, I want to do a couple of more examples where I've got some random problems here that I want us to work on. But one I just made one up. It's from a problem that I was helping a student with in Calculus 2, but I made it into a finite case. So look at this example. This is talking about parity, like we have alternating bits. So here's an example. And the student was working on writing a power series using geometric series. And I just thought, well, I'll just make up a problem in the finite sense. So we have I equals 1 to 50. His problem was infinite, so it was harder, but we still could do this the same way. So we have 1 plus -1 to the I. Okay, so with this example, I would say, well, what's this sum? Well, when you look at this and you think about it, you're saying, well, this is finite, Professor Ron, so you could just break this up into 2 pieces. Well, we could have done that with the problem that the Calculus 2 student was working, but it wasn't. It was a little bit more straightforward to look at it differently in that case. But based on what you're doing and what I taught you today, you're saying, okay, Professor Ron, this is a finite sum, and I can just look at this as 2 pieces. I can add this piece and add this piece and then put them together. So let's do that. And then we can analyze this a little bit. So you're seeing that the sign here is going to jump around, and we'll talk about that. It'll alternate between negative and positive. So we have basically adding 1 to itself 50 times, that's easy, plus, excuse me, I equals 1 to 50 of -1 to the I. Now, when we look at this and we think, is this telescoping, at least in the sense that we think, well, we have to analyze it a little bit. Now, this is just adding 1 to itself 50 times. So this is just 50 times 1. That's easy. And now here we can write this write out a few terms here. So when I is equal to 1, we're going to get what? -1 to the I, which is -1. So we get a -1. When I is equal to 2, we get -1 squared, which is +1. And so we can do that basically 50 times, coordinating pairs each time. So let's see, that would be I equals 1 and I equals 2. And then we can do 3 and 4, same thing. And then 4 and 5. And then keep going down to 49 and 50. Basically, this telescopes, but not maybe in the way we were normally thinking of with the geometric. So when you look at this in the finite case, basically, you're seeing that they all absorb each other. So if we look at the first 2 terms, I equal 1 and 2, this repeats over and over. So we get 25 cases of this, 50 divided by 2. And these are all 0. So this gives us, so you can say 0, 0, 0, 0, etc. So this is 50 plus 0 equals 50. So you have to do a little bit more analysis with this. So another thing that you might want to notice also with an example like this is alternating sign. That's how we define an alternating series. In Calculus 2, an alternating series will be a series that is generated by a sequence that alternates sign, either negative plus or plus negative in sequence. You don't, it's not something that's sometimes negative and then sometimes some of the terms are positive. That's not alternating. The sign of the generating sequence must alternate in succession. So we can see that this is an alternating series. And what's interesting about it is that it's kind of an odd alternating series, because even though we get 0 here, if we had an odd number here, like a 51, the answer would be -1. So it doesn't converge. This is like all kinds of divergent, because depending on how many terms you add, you may get 0, you may get 1, or you may get -1. So it's one of these things where when you start studying infinite series, you have to be really careful about what opinions you make, or what types of deductions that you make. Basically, you can't be too opinionated, or you go down the wrong path. So this will be something we'll study in detail in Calculus 2. But I thought this was interesting. Just remember that when you have -1 to a power, this will just be -1 when n is odd. And so you always have to worry about the parity of this. And this will be 1 when n is even. And notice a lot of times, an odd number, like in trigonometry, we could say 2k plus 1 is odd when k is an integer. And 2k is even when k is an integer. So there's several different ways you can rewrite series and things. But since I actually taught you this way, I think it's easier to break it up and notice that this telescopes. Now, there's some other examples of telescoping that I want to show you that I think are kind of interesting. And here's one. So since we've done telescoping today, and here's another example that I think is interesting. And say we have the following general term, then we're going to do some more applications. We have 5 times the base 10 log of n divided by n plus 1. This occurs a lot in calculus, especially with infinite series and sequences. And so if we look at this general term, ladies and gentlemen, the first thing you can notice is that we could actually use identities of the logarithm to rewrite this. So this would actually be 5 times the natural log of n minus, the base 10 log, not natural log, base 10 log of n plus 1. But now you can see if we do a partial sum, this will telescope, because as we look at successive terms, this will become n plus 1 in the next index and be absorbed by that. So notice these arguments are offset by 1, and that sets up telescoping. So we might say, what is S sub n? Now, you might be thinking, we answered this for arithmetic right here. We answered this for arithmetic. We answered this for, let's see, I covered it up. Here we go. We answered this for geometric, didn't we? Now, the other important type of series is the telescoping one. We don't necessarily have a set formula. We just know that most of the terms will just die off, so to speak. Like here, for this particular number, we get exact absorption, so to speak. All terms die away. So this is something I made up. So you always have to be careful to analyze correctly, because again, don't make assumptions that are invalid. Always write things out to test what you're about to declare as being true. So when we say here, what's a formula for the partial sum here? Well, this is easy because again, we can look at this and see that it's going to telescope. So this would say S of n will be the sum k equals 1 to n. And of course, we've got the 5 here, which we're just going to factor because it's just in the way. We'll get what? Log of k minus log of k plus 1. Now you're thinking, okay, well, notice here, this k, when we've got log of 1, that's going to be a 0. This will never be 1. The least this can be is 2. So this survives, but it's 0. So we can say first, we can factor the 5. And now you're thinking, okay, well, what's going to go on here? Well, notice we got this 5. So let's just write out a couple of terms. So we've got what? Log of 1 minus log of 2. And then we have log of 2 minus log of 3. K equal 1, K equal 2. You see, absorb. So that's what we call telescoping. We keep going. And then we can do n minus 1 and then n. So we can do log of n minus 1 minus log of n plus log of n minus log of n plus 1. So I'm writing all this out kind of unnecessarily, but just to show you that these are separated by 1 unit in the argument. So all of this absorbs. This will absorb in that. Notice here, these absorb. This absorbs in the previous term. The only thing that survives are the extremes. So this is what we call, again, telescoping. Telescoping. That means, and this happens a lot in Riemann sums, using the identities of the logarithm, we've exposed the fact that this is a telescoping sum. And more power to us. And so now we see that we're left with 5 times log of 1 minus log of n plus 1. Well, that's 0. So we just get negative 5 log of n plus 1. That's it. So now you could say, what is S100? Well, it's negative 5 times log of 101. How simple is that? Because it telescopes. N is 100. 100 plus 1 is 101. How easy is that? So when you've got telescoping or you've got arithmetic or geometric, where you can get a real simple formula for the partial sum, which we have here, then your work is a lot less. But this rarely happens. What we usually end up doing with the calculus is that we figure out that a particular infinite series, ladies and gentlemen, converges, and then we can approximate it, you know, to suit our needs. But summing series to get exact values can be almost a tedious exercise, if not always possible. When you study Fourier analysis, you'll learn how to sum some other series using sines and cosines, which is always fascinating. But what my main purpose today is to make sure that you are aware of 2 very important sequences. The arithmetic is fun because the problems are fun, easy to do, common difference. They don't end up in the calculus that much, but the geometric and the telescoping are objects that you will study quite often in the calculus, and you need to be aware of them. The telescoping is such a neat thing. And when it happens, you're like, oh, wow, I got this problem. Look at this. Look how nice this is. This uses our understanding of the identities of the logarithm. So you can see we get a very elegant solution that just seems to fall out of the woodwork. But if you don't look at something carefully enough, you never see what it can do. So word to the wise, use your trig identities, use your log identities. They transform the problem, especially when you look at it and think, what am I going to do with this? So the identities that we've learned will be extremely helpful. Now let's look at some more examples. So you can see I'm a big fan of the telescoping. So study that as much as you can. Let's see here, we've got, that's more arithmetic. I have a couple more examples I want to do with the geometric. Yeah, let's do this. I just start writing and I write down problems and I think about what I teach my calculus students and say, well, these will be important for my pre-cal kids. Again, you'll find a lot of the WebAssign problems to be very simple and straightforward, but that's just to give you a little bit of reinforcement. Now, one thing we can do is use the geometric to rewrite repeating decimals. So here's an example. We'll start out one, and then of course you'll see one of these in your WebAssign, maybe a couple of them. So let's look at this. So consider the following. This decimal. Say we have 7, 7, 7, 7, etc. This is just 0.7, and we only have one repeating unit. So this is a good place to start. So we'll say write as a fraction. Because you know, or at least you know from your math classes, especially in Algebra 1 and maybe general math, that repeating decimals can be written as fractions, as ratios of two integers. The irrational numbers don't have that quality. That is, we can't write an irrational number as the ratio of two integers, because then it would be this. So this is something that helps us to understand the infinitude of the real number system. So when we look at this, we think geometric. So when we think about this, we're thinking, okay, what's the first term? Let's just go ahead and get rid of the decimals. We know it's just 7/10. And then to get to the next term, what do? If we're going to think we move over one decimal, we do what? We do 7/10 times 1/10. Now, the idea is, let me go ahead and just write this as the sum, just to kill two birds with one stone. So I'll just say 0.7 repeating. Just write it this way. I was just going to write down the sequence, but that's just getting beside the point. So I'll say 0.7 plus 7 divided by 100. That'll be this part right here, 0.7. And now add the next one. 7/10, 1/100, like that. Or if I want to be real precise, I'll just say 1/10 squared plus 7/10, 1/10 cubed. So again, that's the 0.7, the 0.07, the 0.007, 0.0007. So here, just go ahead and write this down. This is 0.7. This is 0.07. This is 0.007. This is 0.0007. So what you're seeing here is that this is geometric. So if we want to write a fraction here, we can cast this as a partial sum. Well, not a partial sum, an infinite sum. So now what does this give us? And you're thinking, the idea here is that we have an infinite geometric series. So we have A equals what? 7/10. And R is what? 1/10. And this is infinite, infinite. These are fun. You repeat these again in Cal 2. And again, by then you need the review. So when we look at this, we're thinking this is the infinite sum. So we basically have S infinity. S infinity is A divided by 1 minus R. So equivalently, S infinity in our case will be 7/10 divided by 1 minus 1/10, right there. So simple. Once we recognize, and then of course you can change this up depending on how many different numbers are in the repeating unit. You do it the same way. It's just, this is a good place to start to give you a way to recast this in terms of geometric. And so now we have 7/10, and then of course this will be 10 minus 1, so this is 9/10. The 10's absorbed, and we get 7/9. Now, of course, the idea is here, you looked at this and said, oh, I bet that's 7/9 or something. You probably thought about it. But the idea here is that infinite repeating decimals are actually ratios of two integers. And so the idea here is that when you think about this problem, now you can look at it as an infinite geometric series. So like I said before, ladies and gentlemen, the infinite geometric series is easy. There's no end. It's just A over 1 minus R. Once you have that, this is so much less work than the partial sum that we did, where we have to find the end, then put in the end and deal with all the additional arithmetic. This arithmetic is very straightforward. So again, there's a time when you just, oh, please let this converge so I can use this simple formula. My calculus students are always happy to see this. Again, the geometric series will be important like the Pythagorean theorem. It will become your friend. And when you ever take complex analysis, you'll see it even more when you do residue calculus. And the Laurent series. So it's a nice thing to have in your back pocket. Now, there's one example that I found in the WebAssign that I thought was very interesting. Again, as you work through these problems, work with the famous formulas, manipulating the sums by breaking them up, work with the formulas for the arithmetic and the geometric. Again, the arithmetic is pretty simple, much more easy than the geometric, but again, follow the convention. Just like when you do the conic sections, what I'm noticing is that you have to adhere to the way we've set them up, adhere to the conventions like we adhere to the arithmetic of the unit circle. It's no different with the conic sections. So don't think that someone did this overnight, ladies and gentlemen. People actually do think about this. So embrace it because it's not going anywhere. Okay, so here's what we have. Here's a nice example. We have a ball is dropped from a height of, this is a nice physics problem, of 8 feet. And then it says it bounces up 1/3 of the distance it has fallen. So this is a nice model. And then what the question is, there are two parts. We'll just do the first part and then you can generalize this. It says find the total distance, the ball has traveled at the instant it strikes the ground the fifth time. So the generalizing you'll do, it'll just be for the nth time, which you'll be able to do based on how I show you how to do this. So that's the easy part. This is the harder part. Now, you have to think about a model in this case. So we think about in this case that we've got a ball here and it drops. So it's, we know that under the influence of density and gravity, we have parabolic. Okay, so we basically end up creating something that looks like a cycloid. But for instance, we have some, so there's the first strike, second strike, third, fourth, and then to the fifth. So I'm, not Rembrandt here. So here we're thinking we have the 8 feet. So this is the first strike, the second strike, third, fourth, and then at the instant it hits the fifth time or strikes the fifth time. So the key here is noting our little model here. I think this is a really nice problem. So now when we think of distance traveled, we can look at this in terms of the hypothesis. So distance traveled. You can just add it all up, that you can all, folks, if it doesn't work with the theory, you can always just add it up. I mean, it's a little bit painful though. So now notice we fall 8. So we've got an 8 here. And then the ball will bounce 1/3 of the distance it has fallen. So it's going to bounce up and then come back down. So it's going to travel the same distance. So we're going to get a factor of 2. And then we have 8 times 1/3. So 1/3 of the distance it fell before it hit the first time, but then we do 2 of those. So we got 1, 2. And then same thing again. So this is the first strike. So we hit the first strike and then we bounce up. I won't do that yet. So let's just kind of say we mark that off. And then here, again, we get a 2. And then we have the 8, but now we have 1/3 squared. So 1/3 of that distance, but 2 of them. So check. And then plus 2 times 8, but then 1/3 of that. So we get 1/3 to the third. And now we check that. And then the very last one, before we hit the fifth time, we have plus 2 times 8, 1/3 to the fourth. So each time the distance traveled is 1/3. The distance it bounces up, so to speak, is 1/3 the previous fall. So, but then we have what? Up, down. So you've got a factor of 2 each time. Up, down, up, down, up, down. That's part of the model which most students don't get the first time. This is a train wreck if you don't think about the model here. And now you look at this and think this is starting to look very geometric. So let's rewrite this. This will be an 8. And now this part is looking very, very, very familiar. Notice when we look at all of this, we've got all these 2's here and we've got an 8 in everything. So let's just go ahead and factor because we're lazy. So we got a 16, a 16, a 16, a 16. So let's factor that. And what's left behind? We got 1/3 plus. Now, if you want, you can just go ahead and, let's just do this. 1/3 squared, 1/3 to the third, 1/3 to the fourth. Very nice example. Now notice geometric, fluff, riffraff over here, but geometric. So write that down. Geometric. So now when we look at this and we think about this, we've got 1, 2, 3, 4. So we have A is 1/3. We have R is 1/3, and N equals 4. So now at this point, we can go ahead and figure this out. That's a partial sum. You know, we have to work harder with the partial sum. So this is 8 plus 16. And now we can write the formula for the partial sum. Remember, S sub n equals A times 1 minus R to the n divided by 1 minus R. So let's fill that in. So we've got what? 1/3 times 1 minus 1/3 to the 4th. That's just going to be 1/81 divided by 1 minus R, 1 minus 1/3. So this will be 8 plus 16. So now notice we have the 1/3. And then of course, this is a 2/3. 1 minus 1/3 is 2/3. So the 3's are going to go away. And then we have an 81. So 81 minus 1. So now we have 8 plus, now of course these absorb, the 3's absorb, and then the 2 into the 16 will be 8. And then we have 80 over 81. Now we can get a common denominator, 81. So we have 8 times 81 plus, now of course, 8 times 8 is 64 with a 0. So that's 640. And so that's what, 648, right? Add 1, 8 to it. I guess I could have factored that. You're thinking, Professor Ron, you could have factored that. Well, you know, live on the edge, right? So this will be an 8, and then we have an 8, and then what, a 12. So 1288 over 81. So when you look at this example, this is a physics problem in the sense that we think about the effect of our universe on balls that are dropped from heights and how we have the influence of their density and their gravity. And this is what Newton did. And so what I thought was interesting about this particular problem is that, again, it's kind of like the hypothesis that we used with the layers, the poles, and thinking about how we model the stack of poles so it's geometric. Same thing. And then we look at this and say, oh, can we model this in terms of a sequence that we understand? Now, notice when I first read this problem, you think in your mind, oh, that's geometric. But until you actually think about the physical nature of the problem, the factor of 2 is not really burning into your brain. So this is why it's important to think about the model that we've set up here. And notice, don't try to force the geometric onto any part that's not included. So notice here, we see that this part is the geometric. This is just riffraff over here. We know it's important, but now you can change this problem to have any numbers you like. So what I want you to do is think about how we can generalize this. You can take this formula right here and generalize it for the nth strike and get a beautiful formula. And it will be just like I've done here. So what I wanted to do today is just give you a snapshot of the sequences and the partial sums. The sequences are extremely important, but what they generate in terms of a sum, a partial sum is even more important. But what you generate is a sequence. You generate a sequence of partial sums. And so what we find is that maybe in general, a formula for the partial sum is maybe something that doesn't occur very often. But when you get to calculus, you will use the geometric, you will use the telescoping, and then you will learn particular theory. If someone gives you a series or a power series, the question will be, does this converge or diverge? And you'll be able to answer that question. And then you will be able, in most cases, to figure out the interval on which a particular power series converges. So the prelude to all of that are examples like this. Again, not difficult like the trigonometry. So this is a nice break. And I think it's a refreshing break because these types of examples are fun to do. So I wish you well as you complete your work for test number 4. Just remember that the work on the hyperbolas and the translation of axes and this stuff this will be due into the next week, and then the hyperbolas and translation will be pushed to Sunday. So you just need to take care of the work for the test and get that test knocked out. Again, use Wednesday tomorrow as a flexible day if you need it. I asked some of the students if they felt that the Wednesday would be helpful, and the answer was affirmative. So take advantage of that time if it will make you feel more at ease as you test. But be sure to get that scanned work into me once you have completed the WebAssign portion. Again, I'd say enjoy the nice weather, but I'm not so sure about Mother Nature. But I appreciate your attendance today, and I hope that you're able to get some relaxation. Professor Ron's not going to relax much. I've got plenty to do, but at least we'll be ready to surge ahead as we get back and complete this semester. So everyone have a good day, and I wish you well as you complete your work. Thank you.
Thank you.
Bye, everyone.